Part 2, the ARM architecture. So, the set of instruction and addressing modes available on the ARM processor is closely related to the architecture that you are watching in this image. This architecture provides for certain operation to be performed efficiently, and it has a direct relationship to the types of instruction that are supported. Please note that on ARM, two source registers can be selected for an instruction using the A and B bus. Then the data on the B bus is routed through a shifter and then to the A loop. This allows the second operand of most instructions to be shifted in memory for an arbitrary amount because it reaches the A loop, and then the data on the A bus goes directly into the A loop. Additionally, the A and the B buses can provide operands for the multiplier, and the multiplier can provide data for the A and B buses. Then the data coming from memory and or I/O devices is fed directly into the A loop bus here. Okay, from there it can be stored in one of the general purpose register, one of the many general purpose register, and then data that is being written to memory and or any input output device is directly taken from the B bus here, which means that the store operation can move data from a register to memory, but cannot modify the data on the way back to the memory or to I/O devices. Finally, the address register is a temporary register that is used by the CPU whenever it needs to read or write to input-output devices. It is used every time an instruction is fetched from memory, and it is used for all load and store operations. The address register can be loaded from the program counter, okay, here from the program counter bus, and it is used obviously for fetching the next instruction. Also, the address register can be loaded from the ALU, which allows the processor to support addressing mode where a register is used as the base pointer and an offset is calculated on the fly. After, its contents are used to access I/O devices. The base address can be incremented, and the incremented value can be stored back to the registers. This allows the processor to increment the program counter after each instruction and to implement a certain type of addressing modes where a pointer is automatically incremented after each memory access. ARM processors are available in 32 and 64 bits mode. It means that in 32 bits, the size of the registers is 32 bits, and on the other hand, it's 64 bits. On ARM32, you also have two available instruction sets. You have T32, also known as thumb2, that is a mix of 16 and 32-bit instructions. So it literally, you have a variable length instruction set like x86. Instead you will see that in ARM the size of each instruction is normally fixed, but in thumb32 it's not the case. And then you have the A32 and normal 32-bit instructions, as you can expect. Obviously, you have also the 64-bit version, but please keep in mind that in A64 you do not have thumb. So thumb 2 is also a feature available on 32-bit ARM 32 bits. Maybe thumb, you have already heard about thumb 2, it is an old version. It's an old ISA with fixed 64-bit instruction. Instead, thumb2 is an extension of thumb with additional 32-bit instruction. So you have about the same code density, but the performances are similar to R832. Service information, from now on I will refer to thumb and thumb2 indiscriminately, and the rest of the course is based on AArch32. Okay, unless, I mean, if I will refer to the 64-bit version, I will tell it explicitly, but at the moment this version of the course will not support the 64-bit version. But why thumb? Why they came out with this idea? The goal was to reduce the code size, so to reduce the total amount of memory required to store your program. Because if you're using, a variable length from or 16 or 32, or you're just using a 32-bit fixed length instruction set, I mean, for sure with thumb you will always be the same or less. Another thing, obviously this is very important, but is, quite naive. Only one set can be active on the processor. We will see how we can switch from ARM to thumb, but just one set can be active on the processor, and thumb is a subset of ARM. It means that all the instructions that you have in thumb are also available in ARM. The only difference is the encoding. It means that, as you can see in this table, so for example, here we have the MOV R3, R9 instruction that we have already seen a couple of slides ago. Here in 832 is encoded using 4 bytes. Instead, in thumb 32, we are just using 2 bytes. On the other hand, the BL, that stands for branch with link to this address, it is always encoded using 4 bytes, both in ARM and thumb, but you see, with a totally different encoding. Always keep it in mind that such numbers are expressed or stored in the little endian format. On ARM32, we have 16 available registers. However, each processor mode governs which registers are available. And it means that if you are in user mode, for example, or in RQ mode, you have a different copy of the same registers, in this case SP and ALR. And the reason for having these banked registers is to get faster interrupt handlers and also services, as they can use their own banked register without having to save user mode registers to memory. Let's see more in detail all the registers. So we start from R0 to R10. They are considered general purpose register, even if in the part 4 of this course we will see that those registers actually have a purpose when it's a matter of calling functions. Then we have R11, the base, also named frame pointer, that holds the pointer to the current stack frame. We will see this more in detail later in this course. Then we have the R12, that is the intra-procedure register, and is, a scratch register that is often used by the linker. We'll see some uses of the IP later in this course. Then we have the R13, stack pointer. In this case, we have the pointer to the top of the stack. Then we have the link registers, and this is a very particular register. You don't have this in x86. This register is responsible for holding for storing the return address whenever you use the branch with the link instruction. Automatically, the next instruction, the address of the next instruction is saved to the link register. Then we have the program counter that holds the address of the current instruction. But this is very different from x66. If you are in ARM states, the program counter is is not pointing directly to the current instruction, is pointing 8 bytes far from the current instruction. Instead, it's 4 bytes after the instruction in thumb state, and this is very, very different from x86. Don't worry that when we will use a debugger, the debugger will take care of managing this peculiarity for us. And then we have the CPSR, that is the current program status register, and this register holds processor status, control information, for example in which mode we are running, ARM, thumb state, and so on and so forth. Finally, we have the CPSR, this is the saved program status register, and this is only used and accessed in privilege modes. So for us is just here for a reference. Let's see the CPSR register more in detail. We start from the right to the left. Here we have the processor mode, they specify the processor mode like, user, system, supervisor. Then we have the fifth bit is the thumb mode that specifies in which state the processor is running. 0 for ARM, 1 for thumb. And then here, the most significant bits are the N that stays for a negative result from the A loop. For example, you are subtracting two numbers and you got a negative result. Z stays for 0, and here you got a negative result. For example, you were subtracting two numbers that they were the same. And then we got the carry flag. The carry flag is closely related to the borrow flag, and it's so closely related that they do not use a borrow flag. We just there is this relationship between the carry and the not borrow flag is the fact that when the carry is set to 1, it means the borrow is set to 0 and vice versa. This flag is used when you are dealing with unsigned arithmetic. What does it mean? It means that you have a 32-bit number, you are summing or subtracting it with a 32-bit number, and if you are summing and you get a number that needs more than 32 bits, the carry flag is set to 1. So it means that unsigned overflow happened, and this means that something bad happened. On the other hand, if you are subtracting and the carry flag is set to 1, it means that the borrow flag is set to 0, and it means that it's fine, it's good. On the other hand, if you were subtracting but the carry flag is not set, it means that you needed a borrow, and this is something bad. We will see a table in a couple of seconds. Let's inspect the V bit, okay? The V bit instead means that there was some operation and the result overflowed. The V flag is used when you're dealing with signed arithmetic. And this bit means that in some way, you broke the sign bit. And if the V flag is set, it always means that something bad happened. I hope that this table will sum up what I've said so far in a more clear way. So, overflow flag, if it's set to 1, it's always bad. And the V flag is used for signed arithmetic. On the other hand, the carry flag, it depends. If you are summing and you got the carry flag, the result is incorrect. So you need a bigger number. On the other hand, if you are subtracting and you got it, the result is correct. Okay, so to sum up, the overflow flag always means that something bad happened. On the other hand, the carry flag depends on the operation. But don't worry too much about such details, because the condition codes, so the codes that are checking if you are comparing two numbers, if one number is bigger than the other, and so on and so forth, they are actually checking those bits, but you just need to remember the condition code, for example, GT greater than, and so on and so forth. You don't need to remember all such details, but you need to be aware of them. So I'm gonna open our EVM. I have already started the emulator, and now I'm going to connect it in SSH to the Raspberry. Let's increase the font size. Okay. Okay, we're gonna write the hello string to the screen. I don't know. Raise variable 0 t. Okay. Okay. Now I'm going to compile this source code, and the DCC compiler has created the a.out file. Okay. Let's start this file with GDB. It takes a few seconds. Okay. Now I want to stop the execution to the very beginning, to the entry point, the main. So we can write the main. That means set a breakpoint to the main function, and we run the program. And you see, takes a bit time. Oh, let's zoom out a bit. Okay. You can see here the registers. As I already said, we have our 16 registers. Okay. And here we have the CPSR register. Here we have the stack at the, this is the address that is pointing to the top of the stack, that obviously it corresponds to the stack pointer registers. Okay. And down here we have the code. You have the instruction that we're going to execute. Here we have how many threads we are currently running, and here this is the trace. It means in which function we are at the moment. If I'm going to call another function, we will see here another function. Don't worry if at the moment it looks like very complicated. We will understand more. We'll got more detail. We will go more in the details of GDB later. This is just so that you can have an idea of what's going on, how the debugger will interact with the CPU. Oh, for example, another things that I see here, if you have a look at last thing that we already discussed, we were talking about the CPSR, and here you see, here we have set the 0 and the carry flag. Okay, so when when you see here some uppercase name, it means that the bit here is set, otherwise no. Okay, so I'm done. See you in the next part.